this lecture we will do one exercise, and the most important exercise that one can think of at the very beginning of a course is how to express a subvector space. So we already know in general that if you're talking about general vector spaces, the only way to express a subvector space is to provide a set of generators for this subvector space. In the case the vector space we are talking about is Rn, so an Euclidean n-dimensional vector space, then besides providing generators of it, we can actually describe subvector spaces by means of linear equations. So this is what we are going to see in the next exercise and the following one. So prove that the set given by the n-tuples x1 through xn in Rn, which satisfy the following equation: lambda 1 x1 plus and so on plus lambda n xn equals to 0. So this is one homogeneous linear equation that has to be satisfied by the coordinates of vectors that belong to this subset A. Okay, so this A is described by vectors in Rn satisfying this equation for a choice of lambda i's that are fixed, numbers lambda i's that are fixed. So we want to prove that A is a subvector space of Rn. Now, what's the definition of subvector space? Well, that has been covered in the lecture 4.1. According to the definition of subvector space, we have to check the following two properties. The first one is that if we take any two elements, a1 and a2 in A, so two vectors in Rn that belong to a1 and a2, then if we sum them up using the sum structure of the vector space where A lies, which is Rn, so we sum them up through the using the sum of Rn, we get, of course, another vector in Rn, and we have to show that this vector is indeed in A, not only in Rn, but in A. Okay, this for every a1 and a2 in the subset A. The second property is the following. So we take any scalar alpha in R, and we have to show that if we take a vector w in A, multiplying alpha with w in Rn, we will be getting a vector which belongs to A, exactly like in the situation before. So the first is the property, the first property is called closure under the sum structure, and the second property is called the closure, property of closure under product by scalars. Okay, for property 1 we take a couple of generic elements in A. Since elements in A are vectors in Rn, the shape of these elements are n-tuples of scalars of real numbers, n-tuples of real numbers, x1 through xn and y1 through yn. So to check that, what we have to check is the following, that if we take the sum of these two vectors in Rn, which is this vector, the vector with coordinates x1 plus y1, so on, xn plus yn. So here we are using the definition of sum inside the big vector space, which is Rn. So if we take the sum of these two vectors, a1 plus a2, this case here, this sum still belongs to A. So how do we prove that something belongs to A? We just have to show that the coordinates satisfy this equation. This is the only condition that describes elements in Rn that are in A. So we have to take these coordinates and multiply them by lambda i's and show that this sum equals to 0. So we take the sums for I that goes from 1 to n of lambda I that multiplies the coefficients of this vector, so xi plus yi, and we have to show that this is 0. Now the left-hand side is a number, is a scalar. Okay, this summation is a scalar and can be expanded as, so we distribute lambda I to the summands, so we get sum of lambda I xi plus lambda I yi. And then we apply the commutative property of the sum in Rn so that we can collect all the terms in xi on the left, first sum, and then the second sum comprise all the terms with yi. Now, we have not used yet the fact that x1 through xn and y1 through yn are in A. So far we just expanded an expression. Okay. So now we want to show that this equals to 0, and we have not used that. We have not used yet that these two vectors belong to A. So let's do it now. We conclude that since x1 through xn lies in A, the sum of this big sum here on the left equals to 0 by definition of A. And likewise, the second big sum here of the yi's equals to 0 as well, because again, the fact that this vector belongs to A. So we are summing up 0 with 0 and we get 0. The second property we have to check is the following. If we take a scalar alpha in R and multiply to any vector W in A, we still get a vector that belongs to A. So we take a vector, generic vector x1 through xn in A. We multiply on the left by a scalar alpha. We get the following vector using the product with the scalar structure of Rn. We get the vector with coordinates alpha times xi's. And we have to show that this vector belongs to A. The only thing we have to do is proving that if we take the sum of all the coefficients of the vector, multiply on the left by these lambda i's that we fixed at the very beginning, we get the 0 number. So the left-hand side of this equation, so this summation, can be rewritten in the following way. So we delete the parentheses, which amounts to the associative property. And then we commute alpha with lambda I, and we collect alpha outside the summation using the distributive property. Therefore, the left-hand side of this equation, the summation, equals alpha times sum of lambda i's times xi's. And here now we use the assumption that the vector x1 through xn belongs to A, which means exactly that this summation is 0. Therefore we get alpha times 0, which is the 0 number. Since we have just shown that A is a subvector space of Rn, then it must have a basis, like any subvector space of a vector space. So let's find one of these bases. There will be infinitely many. Let's find one. So if in the equation all the scalars lambda I were 0 for every I, then the subvector space A would be all Rn. That's because, well, the left-hand side of the equation would just be 0. Okay, so the condition for a vector in Rn to be in A would reduce to 0 equals to 0, which is always verified. Therefore, it is an empty condition, and there are no other conditions defining A. Therefore, A reduces to be all Rn. And therefore, we can choose as a basis the canonical basis, for example, which is given by all zeros except one scalar, which is going to be 1. And the place of this 1 just changes with the index of the vector. Therefore, let's assume that this is not the case. Therefore, there will be at least one lambda h in this summation defining A, in these equations defining A, at least one lambda h that will be non-zero. Okay, so now we can explicit the xh in this equation and rewrite the equation as the following: xh equals -1 over lambda h that multiplies the summation over all the indices different from h of lambda I times xi. Now, having the h scalar of vectors belonging to A expressed in function of all the other scalars, we can embed the condition on the summation lambda I xi equals to 0. We can actually embed this condition inside the writing of the vectors of A in the following way. So we can express A directly as a series of unrestricted scalars, x1 through xh minus 1, and then from xh plus 1 to xn, and impose that xh scalar will be equal to the following expression. Now we have no other condition to impose to all these vectors, because the only one that was this equation has been embedded in the very writing of the vectors of A. So A is going to be equal simply to vectors of this form. Having written A in this fashion, we can right away explicit one basis of A. So lemma, a basis AI for A is given by the following n-1 vectors. They all look like a vector of the canonical basis, except that in the h position we have a scalar given by negative lambda I divided by lambda h. So in the first vector there will be lambda 1, negative lambda 1 divided by lambda h, second vector negative lambda 2 divided by lambda h, and so on. Notice that the vector that would correspond to negative lambda h divided by lambda h is not here. Okay, so there are n-1 of them. Now the reference for the definition of a basis is in lecture 5.4. So let's see how to prove this. So first of all, the AIs must all belong to A, of course, in order to constitute a basis of A. And then all the AIs, they will have to be linearly independent, which is the case. It is quite easy to show that they are all linearly independent. So these two facts imply that the dimension of the vector space generated by all the AIs is n-1, and that is a subvector space of A because they all belong to A. So we know that the dimension of A itself is less or equal than n-1, or else A would be the whole vector space Rn. So if A had dimension n, being a subspace of Rn, it would be the whole Rn. Okay, this follows corollary of basic extension theorem, and the fact that A would be equal to all Rn would contradict the assumption that at least one lambda h is non-zero. So if one lambda h is non-zero, in this equation, there surely be some vector in Rn that do not satisfy this equation. Therefore, the dimension of A will certainly be less or equal than n-1, cannot be all Rn. In conclusion, dimension of A must be n minus 1 because A contains a subspace of dimension n minus 1 and the dimension of A is less or equal than n minus 1. Therefore, dimension of A cannot have a dimension less than one of its subspaces. Therefore, dimension of A must be n minus 1. And that proves the fact that AI is a basis by the same corollary of the basis extension theorem. We have n minus 1 linearly dependent vectors in a vector space of dimension n minus 1. Therefore, they are not just linearly independent, but they are also generators.